Yeah. Oh, nice. We're starting to see comments. Hi, everyone. Good afternoon, good evening, good morning to whichever part of the world you're joining from. How are you all doing? I can see that we are probably live on all the channels that we usually stream to, but just to, give me a confirmation. If you could drop a hi or something, it'll be perfect. So I can see comments from YouTube. I'm just checking if we're live on other platforms also, and we'll start off in a couple of minutes. Um, Yup. Excellent. We're live on all the platforms. So, hi, welcome everyone. Thank you for joining in. Hi, Richard. Good afternoon from Ghana. That's awesome. Hi, Gaurav. How are you? I'm Mudat. I'm one of the founding members of DPhi. For those who have been attending these sessions, you would know that this is typically where we invite some of the best AI leaders whom we believe are really great educators to come on board and teach our community about some interesting topics around AI, ML, and related fields. Now, on today's date, we have a very interesting guest, and I'll be introducing him very shortly. Okay, but let me give a quick intro of DeFi because a lot of times we have seen that roughly, 30 to 40% of our audience is new. They may not have attended our live sessions, but they might have heard about us. So I'll just give a quick intro of who we are, what we do. Okay, and then we'll jump right into the session as well. So just let me share my screen. 1 second. Yeah, hi. So I believe you can see this. So today we are talking about this session on recommended systems. For those who have been IML enthusiasts for a good amount of time, for them recommended system is something that they would have heard a zillion times, and it's a very burning topic and a pretty common use case. However, pretty interesting one at the same time. We'll be hearing more about it from Sumit, which is why we are here today. Um, Brief intro about DeFi. We are a global community, okay, and what we do is we create resources around AI, and we are on a mission to teach and build AI for the world. So all our resources that are educational in nature are 100% free, including the boot camps, courses, everything. Um, Talking about boot camps, right? So we have these two boot camps running at the moment. First one is 4 weeks of data science with Python boot camp with IIT Bombay's Analytics Club. It's perfect for someone who's just a beginner in data science. As you can see, the first week is just basics of Python, and the last week is where people will be developing capstone projects and everything. Apart from this, we also have a deep learning bootcamp for those who are more adept in data science. They want to dive more into CNNs, GANs, LSTM, so on and so forth. The crux of every bootcamp is that we will have a good set of hands-on projects to work on, so you'll be getting hands-on learning, and plus we'll also be integrating a couple of live sessions into these. So this is something that is running, and it's closing for registration tomorrow. Okay, so if you are somebody who's interested, so we encourage you to join in for sure. Now I'll circle back to this because this is what we're hearing. This is what we're here for today. So with me, we'll be having Sumit very shortly. For those who do not know about him, Sumit is a senior at the Data and Applied Sciences team uh, at Microsoft Research India. He has been an ML scientist at Geo. Prior to this, he was also working as a data science lead at a robotics startup. What's good about him is he's an absolute enthusiast around AI, loves to solve problems. Actually, he interacts with startups on a regular basis, and on top of it, he's also an educator for various platforms that are into the data science ecosystem, which is wonderful about him. So we are going to have a very seasoned, I would say, educator with us today. So let me just loop him in and say a quick hi and introduce. Let's just loop him in. Yeah. Okay. Hi, Sumit. How are you? You need to unmute yourself. I think you're on mute.
Is it audible?
Yes, it is audible. Yeah.
Hi everyone. Hi Mudit. Thanks for having me here, and I'm delighted to have give this talk to you guys. And hopefully, there's something that you can take away from it, and love to be part of this talk. So thank you so much.
It's our pleasure to have you, and thank you very much for agreeing to be a part of this. We really appreciate it. The community is thankful to you for this. So what I'll do is I'll probably go backstage now. The stage will be all yours. You talk about you'll be giving the session, and towards the end I'll be with you to help you create questions that we'll be seeing from the community. Sounds cool.
Sounds
Okay,
good.
and a quick message to everyone who has joined in. If you come across any questions, any doubts that you may want to ask, please feel free to add them into comment section. There's a team working in the back end at DPhi, so we'll be curating them on a regular basis. So we'll try to pick a question for sure. So do put it across. And yeah, let's go.
Sure, I can share my screen, right?
Yeah, you can do that. Yeah.
Just a minute. Is it visible?
Yeah. Yeah.
Okay, cool. So the topic mostly is about recommender systems today. If you have been a data scientist, you might possibly know about the recommender systems. If you're not a data scientist, you'll possibly get to know what it recommender systems in detail today. So majorly, what is expected from a recommender systems is something which is, why they exist right now in the AI community, and overall industrial usages, implementations of corporate, everything we'll basically be discussing. The major part of this talk would involve more about understanding them. What are they? Where? What are different types of it? What are the pipeline components? Whole of the process of end-to-end recommender systems. Plus, at the end, we'll be discussing something about how they can be deployed and the industry practices that generally be you should follow while developing the whole pipeline. The agenda, the core objective behind this talk is to is to get overview or a bird's eye view or holistic understanding about what a recommender system could possibly do, and how a recommender system could fit in a particular machine learning solution in any of the live applications online, right? And so let's get started. So basically, I'll brief you with the agenda today. So mostly we'll be discussing about some context about what we are discussing. What is the industry usages, how they are right now used. What is a recommender system? Why we are using it? The applications industry, types of it. Then some understanding about each type of it generally being used, collaborative and content-based filtering, pipeline components, sources of data for your recommendation pipelines, similarity methods, evaluation methods, techniques, other evaluation techniques, deployment, and industry practices. So we'll basically talk about each a bit of a detail, and feel free to drop your comments or doubts if you have. I'll be hopefully if someone can notify, I'll basically check on them and discuss, or we can do it in the end. So uh, ever wondered how Netflix predicts what movie or TV show you'll watch today, or how YouTube or TikToks predicts the following video user might want to watch next, right? So we might have seen these sort of things while we basically interact with any of the media applications out there, right? Or any e-commerce applications like Amazon, like they possibly know what we might be required to buy soon. That's why whenever you open the app, there's something new you basically seen, which may be different from what you seen last time, right? So fortunately, this is pure science, not magic, and I'll be basically discussing how science can be used to decipher this part. So the main objective that basically solves this whole of these things that we see out there in the media is basically a recommender system. Everything behind this is a recommender system, and they play a vital role in making users engaged, and making sure that company benefits from their engagement, as well as improve their revenues and sales. So the main problem that we see here is users may confuse themselves due to an abundance of information. So this is generally being seen very recently because of a lot of social media, and a lot of digital implementations of everything right now in the market. So this problem of abundance of information is the recommendation systems are one of the ways to tackle these, right? It's not the only way, but it's one of the way, so that users feel less overwhelmed by this all information, and they can basically make sure that they are channelized to the right things at the right point of time. The resolution that we see generally is help users pick or show a product or item or service that particularly perfectly fits their preference. So if we can help users save this time of going through hundreds and thousands of products, or hundreds and thousands of movie titles or TV show titles, you will possibly save a lot, help them a lot in making sure they're happy with their experience, as well as they get the best output from whatever application they're using. So given that, what is exactly a recommender system, right? What if I want to tell someone about who doesn't know anything about it, possibly hearing it for the first time, in layman terms, is nothing but it is a system that aims to predict users' choices and recommends a product or service that is likely to be interesting to them, right? So this is the whole job of recommender systems, as simple as it can be. If I speak a bit technically about what exactly is it behind, okay, I know, in English language, this is something it looks like, but what is in technically happening behind? So, if I talk in general, 90% or 95% of the applications, it's usually a machine learning based model that predicts ratings or similar items based on users' watch history data or users or items profile, right? So that's basically the crux of whole of the tech that I'm talking about. So if you know about machine learning, AI related models, their implementations, the one of the implementations of them is recommender systems. And uh, they are it's a very wide and evergreen field, I would say, recommender systems, because it recommender systems are is an area of machine learning which involves all the areas of which can involve all the area of machine learning. Like if I talk about NLP, if I talk about computer vision, if I talk about graph ML, if I talk about knowledge graphs, if I talk about traditional machine learning, or even even rule based systems, all of it basically at some point of time can be implemented within a recommender system. So recommender systems, building recommender systems is like an open room of ideas, right? You can basically pick any sort of data related to your product, and you can use it for building a model that basically can benefit in building a recommender system. So this is an advantage of this field among all the fields in AI machine learning, right? The function of a recommender system mainly depends on two kinds of information: user item interactions and characteristic information. So user item interactions basically is information that defines user item relationships, like liking on a Facebook post, liking on a TV movie title on Netflix, or liking on a product on Amazon or something like that, right? Or rating a product on Amazon or movie titles, right? So these are just examples. Like you can use music recommendations, or book recommendations. There are multiple sort of, anything can be recommended, right? So any product can be a form of a recommendation, and there could be a rating or like this, like involved to it. So it's like a user interacting with whatever the items that are there on the platform. Second part is basically characteristic information. Characteristic information is the information that defines the profile of a product or item, or a user preferences, profile and preferences. So basically, this is more about understanding the product as well as the user, so that you can basically hyper personalize the user about their needs, that about their future usages on the platform. So this is more based on that. So given these, I would basically want to show some throw some light on why we are using recommenders, like what exactly are the problems that we are trying to solve here, and are they worth solving. So some of the problem that, like I initially started with, is helping users with information overload. So usually what happens is, with all the application that we are using, we usually think that the information overload problem can be solved by search engines. Like I can Google it out or Bing it out something, and I can basically, they will provide me some content to look at or some solution to look at. But the search engines has different purposes. Their purposes is not to solve the problem or channelize the problem or making narrow down the information, but it's their purpose is to get the relevant get the information which is according to your query. So the information according to your query could be relevant to you, it may not be relevant to you, and they're not meant for personalization of data or content. The job is a bit different than what a personalization system or recommender system do. So that is where we use recommender systems, and that's where they come to existence. Second part is basically increasing the sales and revenue of the companies. So understanding users, like what they need, like if I take an example like ad personalization is a good example when we are talking about sales and revenue, right? Usually if you know that if this user is likely to click on these kinds of ads on a particular website, it will benefit if I show these kind of ad to this user when it comes to the website, right? So having personalizing ad for the particular user based on their previous clicks, based on the information that they interact with on the website, usually helps making those ads personalized, and hence basically generating revenue through those ads, increasing sales, right? What happens is usually like if you talk about example of Amazon, right, or Walmart, right? What happens is there's a lot of content about the same thing, right? If I say a lot of products about the same domain, like if I say shampoos or moisturizers, right? uh, there are hundreds of brands of shampoos or moisturizers that are there in a shopping mall, or particularly on a website, that I might choose from. But I possibly want to you practice or possibly try out different products, different brands, and I don't know what to choose from, right? So it becomes a very difficult job to do it by yourself, given the time and all this product that are listing that are on the websites, right? So having a channelized view about this is something that is most relevant to your usage, or this is something that you might need to try out, given all the worldly factors that could be involved with it, is a good way to improve your sales by through the personalization method. There are a lot of other things, like what next the user is going to buy, that I just discussed, or what is basically their intent in terms of the products that are not they actually bought till now, but they might possibly buy. So all of these things involve some sort of a recommendation algorithm in the backend that is running and trying to predict all the time for this particular user. So this is something done a lot, and this is basically being used everywhere in the industry. So it's not just e-commerce websites, it's not just media or entertainment applications like OTT applications, or not just any other websites. Practically almost every product company could use a recommender. Product company who has a B2C business can use a recommender system. So third thing is basically engagement and retention. So engaging and retaining user is an important factor for any OTT company. If I say Spotify, or if I say uh, Uber, or if I say any e-commerce website, or Netflix, or Prime Video, anything, right? They wanted to make sure that their users keep engaging with the platform, and they just not engage for a short period of time, but they get retained month over month, so that basically these platforms have a continuous revenue from them. So it directly depends on how well the content is on the platform, as well as how well the content being presented on the platform. So the both factors equally contributes in engagement and retention of the customers on those platforms. So just an example by to depicts one of these, like by providing good suggestions either for movies, TV shows, e-commerce items, news website, encouraging the users to stay engaged, so they can so hence they can show more ads, catch more clients, improve their revenues. So usually if it has been seen from one of the reports from reputed orgs, that Amazon repeatedly generate 35% of its revenue through recommenders deployed on their platform. So if the revenue has such a huge chunk coming from the recommender systems, they practically, the people who are building is has their will be basically the most valuable folks on in the company, right? So recommender systems in industry. So mostly, if I talk about some of the stats about the revenues that are coming from different companies through recommender system deployed on their applications, it has been seen that, like I said, for the Amazon's 35% increase, like Spotify almost around 33% increase in monthly subscription, 60% increase in amount of clicks due to recommendations on YouTube, and possibly more. TikTok completely runs by recommendation algorithm that is behind TikTok. So it's like complete whole of its businesses depends over there. Then Best Buy is one of the another e-commerce site, increases revenue almost 23% after deploying recommender and adopting recommender systems. There are a huge array of companies like Google, Facebook, Netflix, YouTube, Uber, Instagram, Airbnb, Spotify, Amazon, Twitter. So they're all basically employing recommender systems on their platform, so that users just don't get lost with all of this information, there, all of this data they're creating on their platform. And it has been seen that 80% of all content consumed on Netflix is because of recommender systems. Similarly, $98 billion revenues of Amazon. So just to get a perspective of their importance in industry is basically being taken as. Then if you look at their implementation and where they can be seen in our regular day-to-day usage of these applications, we can see them almost everywhere over social media, e-commerce platform, media entertainment applications, and great variety of website. Even if we don't see them, they are actually there. So if just a common example is Google search, right? If you do a Google search on the Google app, you'll possibly see these news articles if you have opened that particular personalization tab from the settings. These articles are completely highly personalized to you, right? So they are basically not, they try that these informations are not, very relevant, and they're not just clickbaits. So they try to do it from different angles, like they will enhance the images that has been shown on that particular tile, or they will make the title appealing, or something that basically more interest to the particular users general interest. So if I've been interested in space or tech or AI or politics, anything, I will possibly see a mixture of 20-30 articles on Google Discover tab that will basically highly personalized to my interest. Similarly, on Netflix, you can say because you watched Clueless or because you watched Avenger, you can basically get some recommendations. Similarly, Facebook, people you may know, or LinkedIn job you may be interested in, or Amazon customer who bought this also bought this, and so on. And similarly, like Hotstar shows recommended to you, and so on. So these are basically a lot of industry implementation that we directly interact with almost every day in our life. And there are many more that are already there, which are not seen as a title or something, but they are actually highly personalized. They're trying to make sure they're learning from your own history or your own experience on the platform, and trying to make them improve the next time you come on the platform. So let's learn more about them. So types of recommender systems. So I'll be going through different information about what are the different types, what are they, what they do, and then possibly as we go along, we'll be discussing about some of the industry practices. So major recommender systems are categorized in three broad classes: uh, collaborative filtering systems, content-based systems, and hybrid systems. So usually there are some other categories as well, but majority of it's basically these three. So and there are these are high level categories. There are subcategories of it, which basically each category have hundreds, 50 to hundreds of algorithms that are there in the backend. Like collaborative filtering would have many more collaborative filtering algorithms that are being used. Similarly, content based and hybrids. So collaborative filtering algorithms are mostly based on user item interactions. Content based are mostly using characteristic information, and hybrid systems combine both types of information with aim of avoiding problems that are generated when working with just one kind. So when we discuss each of it, we're discussing about these problems as well that are generated from each of these algorithms, or a group of algorithms, to understand what's their drawback. Because not every kind of algorithm is, or a group of algorithm is made perfect such that it will basically be 100% accurate in whatever they are predicting or recommending, right? So we need hybrid systems to enhance the overall recommender platform. So differentiating between these two, collaborative filtering and content-based filtering algorithms. Collaborative filtering algorithms generally mean any content that is read let's suppose there are two users on the platform, and there is some particular books or some particular content that they're reading, right? And these are similar users. Then if there's any other new content that is being read by one user, I can basically recommend this to another user on the platform. So this is basically a general practice, right? If you know some person who is almost similar to you, right, in your habits, behavior, reading patterns, your daily day-to-day activities and everything, you would prefer to get more recommendations from him than as someone who's basically different from you, right? So because you know that this person same, you have same interest, possibly whatever new he is doing, I could also like it. So that's the same psychological concept over which whole of this recommender algorithm is based on. Similarly, if I look at a content-based filtering algorithm, like content-based filtering algorithm simply looks at, okay, I'm watching a superhero movie, Avengers, maybe I could also like possibly Transformers, right? Because this is something similar, and this is like they're also superhero sort of movies, right? Or action movies, I would say. So any content read by a particular user, if we have a similar content available, I would recommend a similar content to the user. So that's basically all the algorithm that belongs to this particular umbrella belongs to are called content-based filtering algorithms. So uh, going deeper a bit on collaborative filtering, I would basically say that collaborative filtering models utilize user interactions on the platform to filter for items of interest. That means the set of interactions can be mathematically visualized with a particular matrix, where each entry of that matrix I comma j represent the interaction between user I and item j. So the whole objective of this is to predict a rating for a user item pair based on the history of rating given by the user and to the item, right? So this is basically whole of the collaborative filtering algorithm is based on. So we will be going bit of a technical in this front. So if there is someone who basically has some any doubts, you can basically speak up, and we can be or put it on the comments, and we can basically take it up later. So what exactly is this? It's based on two following observations. Like, users with shared preferences are likely to respond in the same way to the same items. Similarly, users who interact with items in a similar manner, for example, buying the same product or viewing the same article, share one or more hidden preferences. So based on these two observations, the whole algorithm is basically based on. So for example, if I take an example of, let's suppose, a user A viewing item 12456, user B viewing item 1 2 3 5 6 but not 4, being because both users viewed 5 items of the same category, it's likely that they will share some basic preferences, right? And so if a user A liked item 4, there's a high chances and high probability that user B also like it. So this is basically if the user were aware of that existence. So this is the whole idea. Awareing of its existence is the keyword, right? Usually you have all the content on your platform, but that content may not be very readily available to you, right? If I say out of 100 movies I like 12 movies, right? Do I know where those 12 movies are there on the platform? No. The awareness of its existence is the whole key here, right? So this is where recommendation engine steps in. It informs user B about item 4, piquing that user's interest. So technically speaking, the task of the model, the machine learning model that we're going to build in the backend, is to learn a function that predicts the utility of fit or similarity to each user using a utility matrix called user into item matrix. This matrix typically very sparse and huge and has removed value. So this matrix something look like this, right? So you have a user and you have an item. This item could be anything like a book or a movie or or a product or anything like that. And this is the user in the rows and item in the columns. So this user, let's suppose, has watched or read or watched this particular movie, right? He has recommended out of 10 as out of 10 rating, right? So similarly, if he has watched this particular horror movie or something and he has recommended -1 and so on, right? So there are each user has some of the other recommendation to each of the titles or movie they have watched, and there may be more. So I've given 6 examples here, right? There may be hundreds of movies which this particular user hasn't watched yet. So what happens to those movies, right? Where I'm going to use that particular data, because I have so much data to on my platform, but I don't know which user should be shown what, right? I can't show the same thing to every user. So this is where their current interest on the some of the titles being used, and current interest and disinterest on some of the titles being used, and in that hundreds of titles or thousands of titles that are there, being looked after and searched after to find the most relevant for this user one out there. Now what happens in the backend of the algorithm technically is this user item and rating matrix, this is called a rating matrix. User item and rating matrix is decomposes into a user matrix and an item matrix, and this decomposition is basically can happen through, which is called a matrix decomposition, or a matrix factorization. So yeah, I'm basically factorizing this matrix into two of these matrices and using that factor as a latent representation of that particular user. So what do I mean exactly by this? So each row represent a user, while column correspond to different items, right? So the vectors or latent factor are generated after when I basically train this particular algorithm. Let's suppose I block this particular item matrix and keeps updating this user matrix, right? Similarly, after using gradient descent algorithm, if you have known about it in machine learning, that gradient descent algorithm do this for you. It blocks this particular matrix updates, and it tries to update this particular item matrix, right? So this blocking and updating each of it happens until there's a minimization of cost function. So that cost function that has been there, that is being trained over that algorithm being trained on, has to be minimum, so that this update of each of these matrices can happen. Now what do you get after this saturized, and what are the factors that is generally called as? So if I look at certain users, and let's suppose these are the movies they watched into. Now these users, we basically get a user through the user metrics, we get user latent features, or I should also call it user vectors, I should also call it user embeddings. So this is something that we get as an output while training that collaborative filtering model. Similarly, if I look at movie latent features, this is what as an output. So what are these features? These features are nothing but a array of whole numbers who are basically represent up this particular user. So if, let's suppose, out of 1,000 movies there on the platform, this user has watched like 10 movies or 12 movies, and this is basically and then what I'm trying to do is trying to put a tag a representation of this user. So I would say, how do I represent this user? How do my machine know that this is the user that is there on the platform? How do my machine read this user in numbers? So I try to put a user representation in form of a vector that is basically being a representative way of that the machine can able to understand this, but this is some particular representation of a user. Similarly, I do it for an item or a movie or whatever it's a product is, and create an item representation or item embedding of it based on user item interactions, right? And given I know some sort of a rating that is there, what I try to find out is, for those cases which I don't have a rating available, I try to predict those ratings based on the existing user factors or user similarity or item similarity, and see what sort of rating could be possible based on these information that I have already available. So types of collaborative filtering. So before I go there, I just need to send this second point, which is like in the matrices, each row represent a user, while the column corresponds to different item. Vectors or latent factor generated are feed into a similarity method called cosine similarity to find the similarity of vectors using distant matrices. So cosine similarity is just an example that I gave, but there are many other similarity metrics that we'll discuss that are being used to basically find the similarity between two vectors. So if I say like vector 1 and vector 2, how similar they are is basically if each of the vectors are above over each other, that means they are highly similar. If they are opposite to each other, that means the angle between them is 180-degree, that means they are completely dissimilar, right? So that's similarity of vector. They present similarity of users or similarity of items. That is basically being leveraged to figure out the most relevant content for the user. Speaking on the types part, there are two types of collaborative filtering algorithm, which is like user collaborative filtering, which measures the similarity between target users and other users and recommended the item that they watch. Second is item collaborative filterings, which measures the similarity between items that target users rate or interact with and the other items. So that's basically the difference. I'll give you a pictorial representation of each of it. So let's suppose if we go for a user collaborative filtering algorithm. A user collaborative filtering algorithm is nothing but a particular user looking at, let's suppose they are buying different food products, right? This is like Homer Simpson, and Homer Simpson like to have pizza and donuts, and they also like chips, right? But I have another guy which is like Family Guy, who basically likes pizza and donut, but he was not aware of the existence that chips exist in his universe. So Homer Simpson introduced that the chips product to him, and I'm sure that he's gonna like it. So that's something. How do we get it? Because Homer Simpson was a friend of Family Guy, and this particular guy has, both of them has a similar taste. So if they have a similar taste, I mean, definitely I could recommend chips to the guy, and he will basically gonna like it. This is how the algorithm is basically working in the back end to make sure that these two different users are benefiting from their interest, and each of their interest, and helping each others in finding more products. Similarly, talking about item collaborative filtering, we basically see that in item collaborative filtering, let's suppose a user 1 likes all the 3 products, user 2 likes product 1 and 3, and user 3 only or you only have tried product 3, right? So given that the other 2 users who are basically similar to users of 1, 2 and 3, basically I'm trying to recommend the because trying to recommend the content that the user 3 hasn't eaten, or what the food that he hasn't eaten to user 3. So I could possibly recommend content 1 to user 3 based on whatever the items that they are looking to buy. So I'm basically we're trying to get an item similarity in this case based on users interaction with these items. So that's the idea. In that case, in the user collaborative filtering, I'm trying to compare with 2 different users. In item collaborative filtering, I'm trying to compare 2 items. But this is different from a content based model that we'll discuss, right? This is coming from user item interactions, the similarity between 2 items, and the content based model is entirely just content rather than any other user being involved in that. So yeah, so item collaborative filtering is a better way of doing things than just content based filtering that we'll get to know as we go along. So algorithms in this area. So if you look at modeling approaches, there's a couple of modeling approaches that is involved for machine learning models that could be used for building a collaborative filtering model. There are 2 different approaches, 3 different categories that I can define is matrix factorization, clustering based, and deep learning based approaches. So matrix factorization based approaches are parametric, and deep learning based approaches are also parametric, while clustering based are non-parametric. What does parametric and non-parametric means is there are parameters to train, there are parameters to tune, and clustering based approaches basically doesn't involve any parameters to train or tune, right? So that is where the parametric and non-parametric classification comes into. So if you look at matrix factorization based approaches, these are mostly machine learning approaches like SVD, like singular value decomposition, or ALS, alternate least squares, or probabilistic matrix factorization, or non-negative matrix factorization, right? Similarly, clustering based approaches, they're like simple unsupervised learning approaches like KNNs or K means, and they can be memory based, model based, depends on what category they belongs to. But these are modeling approaches that you could use to build some of the collaborative filtering models. Similarly, there are some deep learning approaches like XDeep factorization machines, DeepFM, NCF, which is a neural collaborative filtering, similarly GRU, which is rate gated recurrent units for REC. So GRU for REC is these are some of the algorithms that are used for building deep learning based collaborative filtering models. So we will basically touching this and move and go. We could also go for an implementation, but given the time that we have in this session, we could take that one because it will take at least another hour to at least go through those codes, modules, and such. So content-based filtering methods. So content-based filter. So as we go with collaborative filtering, I think you have a fair bit of an idea about collaborative filtering. Let's get a bit deeper into the content-based approaches. So content-based filtering uses item features to recommend other items similar to what the user like based on their previous actions or explicit feedback. To demonstrate content-based filterings, so if you look at this particular matrix in the bottom, like you have a product in the row and features in the columns, right? And what I'm saying is product one has this particular one rating to this particular feature, or affinity, or mostly there's some value for it which basically defines product one more depth in depth. Similarly, feature 4 has 2 or such. So maybe these numbers are basically representing the degree of connection or importance of this feature for this product. So if I say, let's suppose these applications based example, so you have different Google Play applications and you have different categories they belongs to, right? So if I talk about let's suppose some dating app, right? Some particular health or fitness metrics, right? So fitness applications, so these are like mostly health and they're belonging to healthcare sector. So these are like, these two are most relevant to it. Now these are few categories that are belonging to which category this particular application come into in Play Store. But I could take it up as other factors, right? These other factors could be what are the ratings of this particular app, or what are the apart from categories, how efficient they are. Like I could take user feedback into consideration for these applications, and based on this user feedback I could create a sentiment rating about the application, right? This is the overall positive sentiment about this particular application, and I could use the sentiment as a particular feature in it, right? So given that this is a health related application and this belongs to healthcare industry, I could also create a sentiment feature. I could also create other features as well based on different data available for this particular content, and then use all these features to make a representation about this content that I could use for finding similar content for this content. So this is where mostly content-based filtering shines more on for recommender systems. So there are 3 steps that you should majorly follow while building a content-based filtering model. Step 1: select the data and attributes that you want to use. So generally what happens is, let's suppose if you're dealing with movie data, a movie content would have different content metadata, right? It could be actors, genres, director, right? Anything, it could be of that content metadata. Similarly, if we're talking about news articles, like it could be language, article contents, or text headlines, or descriptions, or anything of that sort. So that basically could be a news article, right? So these are basically the attributes that you need to collect from the data that is there in your org, and then use these attributes to filter out which of them makes the most relevance for you, right? Similarly, if I talk about step 2 for it, right? What do I do after I get this data, right? So assuming that you wrote the code, you filter out the data, process the data, clean the data, store it in a database. Now I have, for a particular content ID, let's suppose I can say movie ID or a news article ID, I'll have all these metadata. What I could do next is encode this data. So how do I do an encoding, right? There are multiple ways to encode your data, right? You could use you could use simple vectorization methods like possibly one-hot encoding, or label encoding, or anything of that sort, right? Or possibly use an advanced encoding method, like a little advanced, like document to vector, or or variational autoencoder, or transformers based approaches that are recently being popular, right? So all of these that you can use to encode your data, and then create vectorized features of the product or application using an embedding algorithm combined for all features, right? So this is where the encoding happens. Now the usual approach is you should be basically combining all these features. So either you basically create an independent vectorization for it and then do a combination for it, or possibly try to use an algorithm that basically can use a multiple features as an input and then create a representation of it. So one of the example for that particular approach could be using a variational autoencoder approach, right? Or an autoencoder approach can feed multiple features as an input, and it will train like an X-shaped model, and it will reduce your 1,000 dimensions vector to possibly a 200 dimension vector. That 200 dimension vector could be a representation of all your features that you're basically inputting over this particular model. So that is where you can encode it. Similarly, recommending content is the third part. You have an encoding. Now you know each of the content embedding, right? Now, what do you do with this content embedding, right? I have the vector. I have vector for all the content on my platform. I could use a similarity calculation techniques over the vectors that are generated and start recommending content. So if I'm saying that I have a user one that is watching content 1, 2, 3. I have 10 content on my platform. What are different contents apart from 1, 2, 3? It could be like content 7, 8, and 10 are more similar to content 1, 2, 3. Can I check that similarity? I need to check one similarity with all the other 9 content, two similarity with all the other 9 content, three similarity with all the other 9 content, and then I need to figure out for 1, 2, 3 what's the top most similar 3 items that I could collect out, right? And then I can try to recommend that. So that's basically the step 3 that you can use it on. You can use this for item collaborative filtering, a similar sort of an approach, but there the embeddings that will be generated for items will be different embeddings than the embeddings generated by a content-based filtering approach, right? But the procedure step 3 would still remains the same for it, right? So some of the algorithms in these areas are word embeddings or encoding based method for textual content. So usually, like if I say movie descriptions, news articles, which are all text content, right? If I need to match a news article with another news article, I need to look at its content, right? This news article is about, let's suppose, football, or this another news article is about similar to some other sports, which is like maybe football news about some other league, right? Now these two are different news articles about football, but they are about different areas. Like one is about a manager, one is about some particular matches, right? I could recommend both the art one I could recommend another article if the user has read one particular article on the platform. So how do I do it? I basically look at what's the content in it, like what's basically they're talking about, and how similar this is to another article that the user already read. So I could have to look for textual content there, and basically that textual content will be dealt with some of the algorithms like DPhi, DF, or what to back or dot to back, or transform based embeddings to basically process this text and try to make it in a higher dimensional vector representation of it. Once I have that, all I need to do is step 3. That's it. Content features similarity based methods like leverage a description of attributes from items that the user interacted with and recommend similar items. Similar to the one we discussed, but the core point here is all of this depends on users' previous choices, right? If a user previous choice is not there with you, what do, right? Which is where the most of the research in recommendation systems goes into, like building a method that is robust to avoid the cold start problem, or new user item problem. Like how you can do it, what are different ways to do it, is a different topic to discuss in itself. But cold start recommendations are for those users who are basically trying to come to the platform for the first time, but they're not finding, immediately can't find the relevant content because we don't have any information about them. So how do I do it? Basically, some of the features that we collect while they join on the platform, like their IP, their locations, their language preferences, their genre preferences, as such, Using those limited data, we try to build a recommender that basically at least show the most closely related content that they might have according to what they have preferred. Once they start interacting, now we have the data and we can follow the regular channel. So this is one area that there's a lot of research going on. What's the best method? What's the robust method to go for a cold start one? And it's actually a genuine problem, because users keep on adding on the platforms, right? And having a bad experience initially for a user would actually result in them permanently getting off the platform, which particularly a application owner wouldn't possibly want, right? Or a particular firm wouldn't possibly want. So that is one. Then next is basically deep learning based recommendations. Obviously there will be some deep learning method like sequence, LSTM, such that could be used to create embeddings. These directional models are basically being replaced by bidirectional or no directional models like transform based embeddings. So practically their usage is not very relevant right now, but they are basically can be used for it. Next is pipeline components. So a recommendation pipeline usually looks like this way. So you have certain data sources like from the user behavior platform items data that you have, right? Now how do you get this data, right? Let's suppose if I talk about user behavior, right? User behavior data can be is a sort of data which basically is like click data, yes, simply speaking. So if you're coming on the platform, like let's suppose Amazon, you click on the product, right? Each click that you do on that particular platform is being recorded as a JSON document, right? And that JSON document is nothing but a key value pair document that has been storing everything about that particular user, whether it's demographic, whether what's the content ID was, what time it was, what's the app ID, location ID, everything, right? And that particular is being stored in a some sort of through Kafka or some particular brokering tool that it's basically being transferred to the company's data centers, and from there another pipelines that basically reads that data, raw data, and then churn it out, put it in a databases like Cassandra or HBase or anything of that sort, big data databases, in a particular tabular format, right? And from there the downstream pipelines like pipelines for building for machine learning models starts. So let's suppose I have it in a Cassandra database, or I'm having it in a normal file. Let's suppose I'm not putting in a database, I'm putting it in a Parquet file. A Parquet file would hold all my schema that I'm basically building from the raw JSON and storing it in there. Now I'll discuss about these industry practices that we need to do for building these schemas and making sure they are efficient as well. I'll touch upon those as well, because we basically have a differentiation for it as well, because building an efficient schema is itself a good data engineering job, because building a schema that is inefficient will lead to delays and latency problems as we build our model and pipeline going forward. So every step of the pipeline has to be taken care is done with the most efficient way. So there are some tools like Spark, HBase, Cassandra that you can use from this tab. Then next comes as data processing and cleaning. So it involves like data cleaning, feature selection and engineering, and data storage related parts. So once you know that I have 120 features that are coming from users click data, right? Out of these, I only need, let's suppose, 15 features or 10 features, right? So I could do that feature selection, understanding that cleaning all my data, like all the corrupt data, all the alphanumeric characters, or whatever the data I feel that this is to not be required, can be processed and cleaned, and then using some regular expressions or some pattern based algorithms or simple text based algorithms like lemmatization, stemming, and all that if it is required. And then doing a feature engineering, understanding can I build a different features out of these two features, right? Now this different features can be used for different machine learning model training or building a data for machine learning as such. So I have to think from that perspective from the feature selection part, which feature should be selected, any kind of statistics need to be done on features, any kind of domain expertise required to select these features. All of this comes from the feature selection part. Then comes the storage, where where do I store it? Do I store it again in a let's suppose a file, a Parquet file that's being stored in your system, or file system, or possibly in a database. Like, can I store it in Cassandra? Is it big enough data that I need to store in a file, or is it good enough data that could be handled by a database? I need to think from those perspectives as well here. So if I think that, okay, this is good enough data, I have 100 GB data that I'm processing every day, or this I can only, when I select these files, I can only reduce it to 2 GB or 3 GB. I could store it in my database. That's my database is capable enough to handle that much amount of data. Similarly, choosing the model, like how do I go for this, right? Will a content-based model work, or will a collaborative filtering-based model work? Because, like, let's suppose if I'm saying I don't have enough data for the users, right? I would start with a content-based model. I'll just say that I have 2,000, 5,000 contents on my platform. I'll create a content-based model, find the most relevant content to the content that I have, and based on this, if the user is reading this content, just recommend it to him. But there are drawbacks of it, obviously. Now, so if I talk about content-based filtering algorithm, I'll just talk about the drawbacks as well. So content-based filtering algorithm, the major drawbacks is basically users getting into a feedback loop. Now, when users get into a feedback loop, it it becomes a challenging thing for a user. Like if I say that A is similar to B and B is similar to C, right? And if I'm recommending, let's suppose if user is reading A, I would recommend B, right? But if A is similar to B, there's a possibility that B is also B will also be similar to A. So that means I could also recommend A back to the user. I need to filter those cases, right? Then if I say that I have degree of similarity between A, B, and C is higher. Degree of similarity of A between B with B and C are higher compared to any other, right? So I've been basically every time till the time A, B, and C are on the platform, anytime the user sees content any of A, B, and C, I will possibly be recommending one of A, B, and C, which basically become a challenge for me because the content is not getting updated now. There will be a time of saturation that will come where my recommendation API, like possibly show recommended for you, is not updating that frequently. And this is actually a personal experience when I say I was building a recommender systems, that having a content-based filtering model deployed and keep it deployed for longer time result in our recommendations not getting updated and getting into that feedback loop as it moves forward. So this is something which you need to check out. Similarly, collaborative filtering algorithm has its own drawback. If you have too many users on the platform, the matrix becomes too big, right? And training those users becomes a challenging task. I can't find a user collaborating algorithm if I have 100 million users, because the matrix would be of like 100 million into 100 million, which is like a huge matrix to do that. Like I would need a significant infra, and if you're not working in a big firm which possibly have access to it, you will have problems with it, right? So that is where and there are the other drawbacks as well that you could possibly discuss. Similarly, what you do in this case is you try to build a hybrid model, right? You try to hide the drawback for collaborative filtering. You try to hide some drawback of collaborative filtering through content-based filtering, and vice versa. And then try to build a hybrid model, which is a combination of these two, so that I have a model that basically complements these two algorithms, and then cover their drawbacks. So that's where hybrid models comes into picture. Then there is other steps that generally people use to hyper personalize their recommendations, which is like user and item profiling. So user and item profiling is being done by collecting all the characteristic information about users and the items. So user's character information could be anything, right? It's basically, I would say, his most preferred genre, is possibly his location, his language that he uses on the platform. Let's suppose I have 10 different languages. He generally prefers English, or he generally prefers Spanish, right? So I could possibly use these two languages only for it. Like, so all the attributes that I can collect for a particular user on the platform, and then try to build a particular user profile out of it by possibly creating a representation of these attributes, becomes a user profiling based recommendations. So these are basically used frequently when you want to hyper personalize the content to the user, making sure that the existing recommendations are wearing out, and I to build an enhancement over those. So these are basically employed at that stage of your deployment, right? Similarly, there are similarity methods usually employed. There are many more similarity methods. I'm just taking cosine and Jacquard because the most popular ones to get the similar items or users. Similarly, there are some evaluation method like hit rate, recall, to basically use to evaluate the recommended content with the actual ground truth. So I'll discuss about the evaluation methods and the evaluation techniques as we go along. So sources of data in a recommendation pipeline, like there are what do you feed in your recommendation pipeline? What kind of data that you feed into? So we generally deals with two categories of data sources. Either they could be available to us, or we would need to derive them from the content or the analytic setups of the organization. So one is basically content data or metadata. This basically involves data about the platform content we'll be looking to recommend. Like in this, one of the cases could be like a news data set. It could be its language, article source, text headline, description, article content or age, how old is the article, and all that can be used as a content data or metadata, which is as an input for the algorithm. The another input for the algorithm could be user interaction data. Like this is the data about the user's behavior on the platform, the interaction patterns, and so. And it could be like timestamp interacted on, content view type, or view time, and all those. So these are all interaction data that basically we can leverage directly, that comes from the app into our machine learning pipelines. So we basically had a mention about similarity method in the recently. So what are these? Let's get an understanding about a little bit of the similarity method to understand like how they're useful and where they're used. So similarity methods are important as they led us to the climax of our recommendation model. So cosine similarity measures the similarity between two vectors by taking the cosine of the angle of the two vectors, right? So if you have go to 10th class mathematics or 11th class mathematics, you would possibly know cos theta, right? Angle between the two vectors. If the cos theta, cos, if it's basically in the same line, then it's 1. Otherwise, if for example a line, it's -1. Or if it's vertical, A and B are perpendicular to each other, it could be 0, right? So it depends on what is the angle between these two vectors, and the vectors is already, we understood that we could calculate a vector representation of that particular user or item, and we can calculate a cos theta of it. If we say cos theta is 1, that means they're perfectly similar. -1, they are completely opposite to each other, and so on. That's basically one of the most used similarity method. So now if we talk about Jacquard similarity, Jacquard similarity measures the similarity between two nominal attributes by taking the intersection of both, dividing it by their union. Very simple example I'll give is JAB is like A intersection B upon A union B. That means like if I say A is an array of items 1, 2, 3, 4, 5. B is an array of items 2, 3, 4, 5, right? So what is intersection between them is 2, 3, 4, 5. What is union between them is 1, 2, 3, 4, 5, right? So I'll calculate a score between calculating these two arrays A and B, and calculating the similarity between them. It's that simple. It's like the most, you can even create a simple basic recommender just based on Jacquard similarity. So it's basically used very frequently in early stages of much early recommendation teams who are basically just starting with these deployments and setting up their deployments. Evaluation methods, right? Evaluation is an important part of understanding how good are your recommendations. Without evaluations, machine learning techniques are useless. So you need to understand how you're evaluating to make sure that they are good enough, or you're not just beating around the bush. So the more recommendation approaches are proposed, the more important their evaluation becomes to determine the best performing approach and their individual strengths and weaknesses. So at some point of time in your recommendation team's maturity, you will reach to a point where you need to set up a robust evaluation method. It usually what happens is in a recommendation pipeline, before you even try to write a recommendation algorithm or try to train a recommendation algorithm, you first create an evaluation method. That's the first step that you do, right? Because you should know what are the business metrics business cares about, stakeholders cares about, and based on those business metrics and stakeholders, you try to create an evaluation metric that let's suppose I want whatever I'm recommending, almost 90% of the users should click on it, right? That means I need to use a evaluation method called hit rate that will give me that particular sort of information. So I need to build that. Now once you build that, you do a pull system. You use that hit rate method and try to look for best possible recommendation approach that can satisfy that particular business objective that you have set it up, right? So evaluation methods always comes first. There are various ways of evaluating a model as well. Online evaluation, so what I was talking about, mostly offline evaluation, but online evaluation happens after deployment. So online evaluation, offline evaluation. So online evaluation recommendation are shown to real users of the system during their session. User do not rate recommendations, but the recommender system observes how often a user accepts a recommendation, and acceptance is the most commonly measured by click-through rate. So you might have seen learn about click-through rate. That's basically the ratio of the clicked recommendations over the recommended content that has been there, and then using that click-through rate, you basically determine how oftenly the recommendation being accepted by the user. So general practice is to set up a A/B test to identify the algo performances. And A/B testing is itself is a different topic. You basically look at some particular segment of the user first, like 5-10% of them, and then try to deploy the whole of it into complete all set of users. You see that in 5-10% I have in 10% I divide into 5%, and then I'm trying to test two different algorithms and see their performance over their 5%, choose one, and then try to deploy the one algorithm over the whole of my 100% population. So this is like a basic idea. There are a lot of other complex approaches, like using a reinforcement learning bandit algorithms to find out A/B test, A/B find out A/B testing outputs, which are basically more adaptable to the environment. That means your recommendations will also be affected by continuously continuous evaluation that is happening, and continuous updates that are happening. So there are more dynamic approaches. There are usual statistical approaches also. Offline evaluation, in contrast to user studies and online evaluation, offline data sets are considered as a ground truth that represent the ideal set of data to for basically testing your models. So if I say that I have a ground truth, that means I know that if this is the user one and this is the item one he has watched, and I've recommended him item 1 to item 5, right? That means in when I recommend item 1 to item 5 in that particular order, item 1 is being seen, right, for this user. And then I try to have these ground truths for certain set of user, such that I have this data build, and then use this data for evaluation for my new algorithms or any algorithms, that does my algorithms trying to satisfy over this case. So is it recommending item 1 to 5, or is it recommending item 5 to 10, the new algorithm? But if it is recommending item 5 to 10, and item 5 to 10 is not even item 1 is not even item 5 to 10, that means the recommendation that I did for that particular user through the new algorithm is incorrect, right? And there are other ways to judge all these things as well. So there are certain evaluation techniques that we use in offline evaluation cases, like flat and no rank metrics techniques, which are basically mean average, MAE, or means absolute error, or RMSE, like root mean square error or such. These are accuracy based metrics. Similarly, there's some decision based metrics as well, like precision, recall, F1, and so on. Similarly, there are some rank aware evaluation metrics, like binary relevance based metrics, like mean reciprocal rank or mean average precisions and such. Similarly, some hit rate and NDCG, which are like the most commonly used rank aware evaluation metrics. So why they are called rank aware evaluation metrics is because they it matters to them that in what order you're recommending the content. Usually what happens, if you open your Netflix, there's a tray that is there that recommended for you or such similar, right? So in that tray, the you have to scroll it left to right, to see the content. But if I'm saying that the content that I'm showing on the home screen, where you have first two tiles that I can see, or half of the third tile, if the first two tiles are the most relevant ones, the user won't have to scroll it to the left and right for it, right? So the ranking of where I'm placing the first item and where I'm placing the second item for a particular user becomes important. So these rank-aware evaluation metrics are more frequently used while evaluating a recommendation engine than flat and no rank metrics. Similarly, deployment is obviously an important part of it. You don't just make recommender systems just for fun or just for having a practice exercise or doing it for fun. Obviously, you should do it for fun, but make sure you do it for making business for the companies as well. So usually, what it means is your input should be given as an output, to that particular as a your output should be given as an input to that particular application where it's being deployed. Now, what happens is there are a couple of ways to deploy recommendation models. I'll be taking the most frequently used ones. Like one is basically deploying on Kubernetes. So Kubernetes is a I would say part of ML ops, which is a new term called machine learning operations or development operations. You generally say the Kubernetes is a platform of orchestration of Docker containers, right? It basically holds pods which are basically auto scalable based on the request and demand and load, and these are scaling up and scaling down depends on it. So it's a platform where what you essentially, so how does the flow happens is, let's suppose once you have your model built, you have basically trained your model or such, and then all you need to do is push your model to deployment platform. So your deployment platform could involve Kubernetes. So how you do is you take you push your code to Git, and from Git you go to Jenkins, like connect your Git to Jenkins, which is called a CI/CD, which is continuous integration and continuous deployment, and then connect your Jenkins your Jenkins will connect it to the Docker containers that are there, that has been created in Kubernetes platform, and these Docker containers would have your models mounted and the metadata that is required by your inferencing APIs, inside your Docker containers, and these are basically being allotted some Kubernetes pods which are basically scalable, and those configuration and configurable, which they can be configured from the backend. Now, what does your Docker container contain? So Docker containers are usually nothing but shipping containers. Like if you have a shipping container, what do you do in a shipping container? You put your container on a ship, and it will go from one port to another port, right? So this is what is happening in Docker container. You pack all your dependencies, you pack all your model artifacts, model outputs, codes that are being used in a complete repo, and the output and input of it into a Docker container. So everything is packed in it. So Docker container is like a mini VM, which is basically holding all your dependencies, all your code, all your model artifacts and everything, or whatever slight small metadata or data or configurations that you need, right? And then it could be that container or file, it could be hosted anywhere. So you just take that container file and then go to a different platform and start running it, and it will basically pick up all the dependencies from internet, all the whatever the data you need, or your model artifact, everything, and then start running there itself. So it makes your model, it makes your whole system very convenient to deploy, right? And now what happens is these Docker containers being orchestrated on Kubernetes. That means there are multiple Docker containers that you could create for each of your small application that can talk to each other, interact with each other, and then take outputs and inputs of each other, right? And what you essentially do is, let's suppose you have heavy models. You have a model that you train, it's a 5 GB model, right? Now you can't put a 5 GB model in a Docker container, otherwise the file will be very big. These Docker containers are already heavy, and putting this big of models is really difficult. So you generally, what you do, you have a network file system that you mount to these containers that will basically holds your that network mount. There's a port open between each of it talking to each other, and this network file system, which is like TBs of storage, will hold your model, and then whenever the inferencing comes up, it will pick this particular model artifact, start reading it in your inferencing code, and then whatever the output of inferencing code, whatever the other input it will require. Let's suppose it requires connection with a external database, or connection with a database like MongoDB that is created on your Kubernetes platform itself. It will basically fetch all this metadata, use a model inferencing code, use whatever the input query parameters that it need. Like, there's an API hit coming, and it gives us user ID and location of user. All of this is basically put as an input in an inferencing code, and the output is basically given either in the form of a API output, or it may be stored in a database, which could be picked up later by another API code, which gets which basically forwarded to the backend team, which deploys, which basically as an input to them, and which basically they will forward it to the application. So all of this basically happen through your Kubernetes. So you need to have a basic understanding of Kubernetes as such to just to get interactive with it. You don't have to be very expert in it, but having a basic understanding generally helps while deploying a machine learning model. Another way is creating a Flask or Fast API based deployment. So you basically can choose a server or something where you basically host your code as well as your API, and then your model artifacts, inferencing code, everything, and you will make a connection with your DB, or which basically maybe on another cluster or on AWS or anywhere, and then use that Flask API to get a request directly from the backend team or from the application, and then send a response for it. Usually, this has been also encountered with a Nginx load balancer in the middle. So let's suppose you have a high amount of requests coming. Let's suppose 5,000 requests per second, or 8,000 requests per second as such, or even more, right? In those cases, there's a load balancer that needs to be there, which basically interacts with these servers, and then make sure that they have an appropriate load that is coming to it in an API, and then the response is being sent the backwards the same way. So all of this basically happen either on one particular single server deployment. So these deployments are not very scalable, because once these RAM capacity, let's suppose there's a high amount of traffic load coming in a peak hours, and once the RAM capacity or the processing capacity surpasses, your API will start to fail, giving 502 or different sort of errors that comes into. So deployment becomes depends on what scale are you deploying. So usually if I'm deploying at 100 million scale, even Kubernetes becomes challenging. You need to basically add a lot of pods, add all that, making sure that inferencing is done in a parallel way. You might also need a Spark for processing. So Spark on Kubernetes is basically a new API that generally comes up, that basically process big data and all that. So having a deployment on Kubernetes can handle that amount of load, but it's not it's not that it can't. It will go on. It will have a limit as well. Then some of the industry practices for each of these stages of machine learning based recommendation model pipelines. So some of the industry practices starting from the data engineering front. So whenever you start building a machine learning model, you'll have some sort of a data engineering needs to be done, right? Before you even, so that you can get your data, process your data, and store it somewhere in an efficient way. So if you are dealing with big data, then data engineering becomes even more crucial. How you are processing your data, is how you are basically storing a data, and what amount of data you're storing becomes important. Because let's suppose if I'm dealing with 1 TB file every day, right, that I'm processing and storing. Now, how much amount of data do I need out of this 1 TB of data that I'm raw data that I'm daily getting? It becomes an important part, right? If I have to pick up 5 fields, I'll need to choose which 5 fields I can pick up. I can't just store some of the fields in buffer thinking I might use it later. So that's basically reduces performance as well. So what is important here is your read and write times. If I'm reading from a particular file or database, I should be reading it efficiently in the low latency way. Similarly, if I'm writing in a database, I should be writing efficiently in it. So what comes important in your reading and writing is how is the schema built, right? If I'm building a schema, taking care of my primary keys, clustering keys, and as such, I would basically create a faster write time or run time, right? Similarly, the jobs that are reading or writing, like let's suppose I'm building a Spark job that's basically reading and writing data, right? How efficient is that job in a pipeline? If it's is it let's suppose take 40 minutes to read and write and process 1 TB of data. Can I make it to 15 minutes or 20 minutes? And these are actually happens in industry. You basically have some Spark techniques, efficient Spark techniques that you could use to make sure that whatever the big data processing that you do is basically done in the most efficient way, right? There's these techniques could be how the process flow, data flow is happening. Is there any skew in your data that is taking a lot of time in the whole stages that are basically being processed while your data is processed? Or is there any the way that you are basically caching your data, or the way that you are uh, writing a select query anywhere in your Spark job? All of these things matter while you are basically doing a data engineering part of your model pipeline, right? Making sure that each of these steps are done efficiently, having those best practices becomes important part. Second comes as the model research and development. Now, this depends on the team stage or maturity in the organization, product readiness, and the experimentation culture. So, not every data science team work on implementing research papers and then building algorithms and deploying those algorithms, right? Some data science team has a business connections, or machine learning teams has business connections, which basically have to be put in priority. Like they want, there's a product whose readiness is there for deploying machine learning solution, but they have limited bandwidth. They want it to be done in within 2 months or 3 months, right? In that case, I can't work over a research paper and then trying to deploy the recommendation model by building those algorithms. I need to use a quick ready solution, maybe like an existing algorithm that is already there, and then deploy it for the first go, and then possibly see what's the output that I'm getting from the product. Based on it, I could research on the papers after that. So having a machine learning, having a initial feedback from the user really helps deciding on which direction should I do my model research into, or algorithm research into, or what sort of papers I should try to work over to make sure that kind of that kind of experience that the user can get. Usually understanding the user in that front comes in handy. So all of your exploratory data analysis, all of those things that generally comes up before model building comes in handy while started working on a machine learning model. So some practices that basically comes is don't just read the paper, start implementing or looking, or don't just read the paper or start implementing or looking for code. Connect your business problems for the most viable solution, right? Let's suppose your business requires you to do something else. It doesn't want it to do what a usual recommendation algorithm do, right? That just show some list of content and it will start. If the user starts hitting, that I'll consider that as a success. Maybe they want something else, right? So having connecting a business problem, first understanding it deeply and then look for the most viable solution becomes a better approach, better practices while you're working in industry. So it may also mean that employing a solution which may not be the best one out there, but it works for your case, so you're basically taking it. So not the best paper or the best algorithm works all the time for every use case. It may work for a general use case for that particular area, but it may not work for your own problem statement. So never be in that particular policy. Second is productionization. Is if productionization is priority, building simple models work. Usually what happens is directly going for a deep learning model with some data scientist. Usually, you will build it, but trust me that you will basically find a bottleneck later, because you don't have the all of the pipelines stable in your system right now. So if your recommendation team is trying to build their first or second solutions, then What you need is a stable pipeline that can be scalable in the future. So if I say that, hey, my products are like 100 million or 200 million or 500 million scale, right? And I want to deploy my machine learning model at that particular scale. You When you deploy that particular model, you have that deployment mindset. You first look at your productionization pipeline, right? You see where and how I could deploy that particular at that particular scale, at that particular traffic, and with the most amount of availability and in my pipelines, right? So having that machine learning engineering strong becomes a challenge, becomes an important part before you even start building your machine learning models, right? Usually what happens is we start building our data engineering pipeline, start building machine learning model research, and completely forget about how will I even deploy it, right? So you build a fancy of deep learning model, and you don't and you basically fall into a place where you don't know how to make sure that this model can be deployed, and you end up having facing problems in a productionization part. So keeping an interaction with your machine learning engineer and making sure that the whole of the model pipeline is in complete sync, uh, it becomes an important part of your job as well. Going forward, third thing is the model deployment part, right? So this model deployment part depends on scale a lot, right? Usually some mid-sized companies or startup companies may not have that much amount of scale. Like they just have like 10,000 users or 1 lakh users or 5 lakh users, or maximum like 3 million users, 5 million users, right? They and that deployment of machine learning, and based on what how much traffic you are getting over that on that deployment, maybe it's not like just users hitting the pipeline, maybe just putting a solution that is that may not be hit too frequently by the user, but it's required on the platform, may also be there, right? So deploying machine learning at a 10,000 user scale is entirely different from deploying it at 100 million user scale. So the infrastructure is completely different. The infrastructure depends on the scale, the how much estimation you need to do, all that estimations as well, that how much year on year growth I'll have from the user, right? If the year on growth is faster, I need to make sure that the infrastructure that I'm building lasts for at least a year, right? After I scale up. But and what happens is, let's suppose you put an infrastructure at today's scale and you forget about the future scale, and after a few months your solutions start breaking, right? So you need to think from those perspective as well, that this is the infrastructure that I would need, this many amount of GPUs or servers or whatever you need, or CPUs for inferencing I would need before I even deploy this. You need to make sure that procurement there is there, and that code is also that scalable and parallelized, such that it could handle that setup on infrastructure. So the best passage should be, you should always be in sync with the earlier blocks in your pipeline. Second is anticipation is key. Thinking before and holistically about a pipeline will help you get the idea about how will deploy at this scale, how will the deployment at scale look like, and or handling the model and user request complexities. Fourth thing that comes up is model monitoring. So set this up immediately after deployment to have a peaceful time ahead. Definitely. So your model has been deployed, right? Now what? I would be requiring it to monitor it as well, right? That's where the actual game starts for. Once your model get deployed, there's the hundreds of challenges that you see, right? Your offline evaluation might be good. You might see that this is a good enough model to be deployed, but what you see on the once it goes into a live environment is it's failing on different because the distribution of data has been changed. There's a data drift came, there's a concept drift came, and because of this the distribution of data changed, and because of which whatever the inferences my model is giving is not accurate, they're highly inaccurate, they're not hitting too much, and your performance is degrading, right? That may be the worst case scenario that you need to think before after you deploy it, right? So keeping those worst case scenarios in mind, you need to keep a monitoring system in pipeline, right? You need to make sure that whatever the inferences that you give is being recorded, it's stored somewhere, those inferences being regularly evaluated, checked if the model is performing well. There should be a certain threshold, a business metric that it is sent, that
my model can't perform lesser than 70% accuracy or so, and these has to be connected with a certain dashboard which take, gets the data regularly for you, right? All of this monitoring system has to be built after deployment, making sure that this is there. And if it's more, when is the model failing, making sure that all of that information, that this is my model, this is why my model failing, this is the reason that is failing, all of this has been reported to you at the right time, it becomes crucial part of a job. So having having that continuous monitoring of model performance, model degradation, accuracy, metrics and such becomes an important part while you are deploying your recommendation models. So this is also something that you do consider. So this is an end-to-end part of it in a top overview. I would basically, sorry if it's extended a bit, I would like to invite if any questions are there with anyone. So thank you so much for listening with patience.
Okay. I think there's nothing to apologize about this. We are just super thankful to you for being so kind enough to. Okay, can you hear me? Am I
Yeah,
audible?
I can. Yeah, it's a little
One.
breaking. Can you hear back? Okay.
Just give me a moment. There is a stormy weather at my place. Just a moment. Yeah. Can you hear me now? Maybe in that case, I won't shift my
I,
Wi-Fi.
I can hear you now. Yes, I can hear you now.
Okay, awesome. ठीक है, बढ़िया है. So thank you, so much for this elaborate presentation. It clearly shows that you have been super kind enough to cover end-to-end spectrum and help people learn. There are a bunch of questions that we have received. We'll quickly pick them up. So there is a question that Ashish had asked. Can you provide some resources to refer for solving cold start problem? I mean, do you
Definitely.
have
So
any
there
resources?
are, I don't have it handy right now, but I could share it with you with the team as well. You can basically get it out later on. The some of the places that you can go for, it's looking out for some of the research papers that basically been there. You could go look out on GitHub. You'll find a lot of cold start recommendations repo where you can get a lot of different algorithms. There are a lot of content that been researched over in cold start algorithms. So just search for GitHub and cold start as a cold start recommendation. You'll find an array of algorithms that are there. You can go around their documentation, you'll find a lot of content, but I'll definitely share some of the contents on the chat if after this. So
Okay. Next question that Rushabh has asked. This is um, not directly related to this, but yeah. So how do we start using big data as a beginner? Let's say for practicing a pipeline, or if I want to learn Spark, where do I get the data set and make a simple pipeline?
so uh, so you will get a data set a lot, right? You will basically find, if you want data set, you will find data set in Google data set research, right? And there are a lot of other similar places where you can get data set that you need to test your data over. So data set would never be a problem for you, given that there are all of these available in the market and they've been open sourced. Second is learning the skill, right? So if you want to learn Spark, make sure that you are at least good enough with SQL before you go for Spark. So you need to make sure that your SQL queries are whatever the SQL concepts are there, they're at least good enough to make sure that you're able to do a simple querying and such. And once you are basically good enough with your SQL basics, or good at least at a moderate level, go with Spark. So Spark involves two different languages like majorly used, which is like Python and Scala. Given that a lot of data science is in Python or machine learning is in Python, you should start with PySpark. PySpark, learning PySpark, you can basically refer any of the online YouTube tutorials or some of the courses that are there on most of the platforms. Most of the courses will teach you at least the all of these contexts related to how to build, how what are the different APIs that are there and all such. But make sure once you study it, after that learn about the best practices in Spark, because Spark is a very tricky area, right? You can build the same thing with a 2 hours efficiency, and you can build the same thing with a half an hour efficiency. So it hugely depends on your skills, SQL skills. and making a simple pipeline would be difficult once you get this data from. I think Google dataset research is a good place. So that will be that. Hope that answers the question.
Yeah, I think this was a pretty elaborate answer. Thanks for that. Also, I mean, a quick shameless plug here. I mean, DeFi all resources are free here, but so there's a data engineering bootcamp going on right now. So even there, you want to learn about these concepts, you can probably explore that. It's built by some of the best data scientists. One of them was with us in the last session, Alexi. But yeah, so that's just one of the resource. Next question that I want to pick is how can we improve the accuracy of recommendation systems?
Right.
Yeah,
So, recommended system accuracies are largely depends on your, you know, it largely depends on how well are you studying the current data or the current feedback that is coming from the user. So, uh, usually, what happens if you deploy a simple model and you get some certain amount of output from it with certain amount of accuracy. Let's suppose I'm getting a 60% hit rate out of a simple model, right? Now I want to go to the next level. Now, in that case, recommendations are hugely dependent on the application, domain. If I'm saying that I'm deploying an application which is highly dynamic. If I'm talking about application like live TV platform, like live TV platforms are highly dynamic. So understanding the those domain about that what is basically being more important these days. Like you have to build a system that basically takes care of all of these. Like you can build a hybrid algorithm which basically combines your popularity metric, your demographic metric, your content filtering, your collaborative filtering, plus some sort of a worldly, importance, right? If I say something like IPL matches are more important these days because they are becoming more frequently. Maybe I could put some sort of weightage with a user profile that this user is a sports user, and then I should basically take that context and take that context in your recommendation list. So all of these basically comes up once you have a better understanding of your application and how efficient you can build that particular model. Usually, going for a hybrid way of building a model is a good enough start. I think that answers if that answers the question.
Yeah, am I audible?
Yes, ma'am.
Okay. Yeah. Thank you for that answer. I'm so sorry I got distracted towards the end since my net is super flaky at the moment. But yeah, I think Destiny is being both supportive and putting up challenges as well. There's a question that one of our community members have asked. So how often do we train a model, and how does someone like Netflix and Amazon go about it?
Right. So training a model again, like in the last question I said, like training a model, improving a model depends on your application. So if I'm saying I'm building on, let's suppose just take an example of what you mentioned, like Netflix. So if I'm building a model for Netflix, right? Netflix has a static content with me, right? So the content, if the nature of content is static, the content is going to be there on the platform sometime. I don't need a quick retraining of my model. I could basically train a model after a month or two and still be good with it. Or there may be cases when you're dealing with dynamic platforms where the content frequently changes, right? And there, keeping a model for a longer time without retraining becomes the model getting stale and not performing well. So there, I need to basically train it like every 15 days or every week or something. So that depends on one of the domain where you're deploying your recommendation model. And how does someone like Netflix or Amazon go about it? Well, places like Netflix and Amazon, they have a huge amount of scale. So, training a model, basically they might use, they basically generally used, some a cluster of GPUs to train that many amount of users. Let's suppose if you have talk about Netflix, there are like somewhere 150, 200 million users that are there, right? So training a model largely depends on, what distribution that you're picking up for your model. Let's suppose if I say I don't want to train my 200 million users, right? I want to train just on 20 million users. But if I can pick those 20 million users out of my 200 million users, I would have good enough representative data set for my model to train it to, and that I could use for training the model. I could use less resources to train the model, and I could use, let's suppose, if I need 5 GPUs, I could do it for 3 GPUs and be done with it. So all of that, usually work in a mostly in a parallel processing, and the parallel processing is mostly the general way to scale it, doing machine learning model training at scale. So I hope that answers the question.
Yeah, there's a question that, I mean, by the way, how much time do we have? Because I mean, do you have time for or for 3 or 4 more questions? Because
Yeah, I'm
people are
good with it. No
okay,
worries.
awesome.
I'm good.
So Anuran has asked this question: won't a hybrid model have varying performance over time, depending on the number of users at a particular time?
Right. So generally what happens is a hybrid model has to be adaptable. Like a hybrid model, something usually takes care of multiple aspects of your data, right? So if I'm saying that number of users at a particular time is it an important metric that you need to consider while building a hybrid model, that I need to add a separate filter out for it. Let's suppose if I say, um, at a particular point of time, I'm getting, instead of talking asking about number of users, I should ask about how many number of new users I'm getting in my platform. Like what is the adoption rate for my platform? So if I'm saying, let's suppose every month I'm getting 20% new users on the platform, that is where will my hybrid model perform in those case is a question. Where, because number of users could be anything, hybrid model is generally used to make sure that the performance for the recommendation improves, and generally the performance degrades for new users because there we don't have much information. So building for the segment of users who are going to give you the hard time is a better approach for building a hybrid model. So I would say, it might have a varying performance, but it has to be adaptable based on that. So I might have to give a, let's suppose, higher weightage to a content based model in those cases where I have a higher adoption rate, compared to cases where lower adoption rate is there, where my collaborative filtering model will shine. So that, I hope that makes the point.
There is one question that Ashish has asked, and it's kind of answered, but yeah, I'll pick this up because the latter part is slightly maybe different. So yeah, can you explain how large scale recommender systems work? I mean, from infra side, I mean, how to train recommender system on distributed systems, which algorithm to use? Yeah.
Right. So usually it depends, right? Let's suppose if I'm saying, like, some organization use CPUs for training, some organization use GPUs for training, right? So if I'm just using CPUs for training, I know that I don't have access to GPUs because GPUs may be costly. They are more the procurement is difficult. I might need to deploy a solution or something. I already have too many amount of users. What I could do is, let's suppose I'm doing it on GPU, like I need to make sure that the framework that I'm building my recommendations on should be compatible with multiple GPUs. So if I'm saying that I need to do a distributed training, I need to make sure that that distributed training is being implemented with that code. That means I can't use just simple Python to just train my model, because it won't work on 4 different servers or 5 different servers that I need, right? So I might use a framework like Spark, right? Spark could be used. What I could do is, the algorithm that I'm using, right? Spark has a Spark ML API, where, although it has limited algorithms, but I could also build my algorithms over Spark. That means, let's suppose I use a backend. I'm basically trying to build out some of the codes that basically can work in a parallel processing way or over Spark, and use that code for training the model for, let's suppose, image recognition. Recently they have Spark 3.0 and image recognition capabilities as well. So almost all of this is there, but most of it, some of them is missing, but you can basically use it for CPU distributed training. Now, on those cases, those frameworks, usually Spark is a go-to way. Those frameworks helps there. But let's suppose if I take from the infrastructure side of GPU, right? If I want to train it on GPU, I could use any of my deep learning frameworks. Like I may not possibly try to get it in a simple machine learning algorithms, like training a scikit-learn on a GPU, right? That will be some sort of work. I need to basically
may see that my scikit-learn can be penalized, and then I can use it over GPU with some fixes over my Spark code or something. Then I could try it out. But usually deep learning frameworks like TensorFlow, PyTorch, Keras, they are compatible with training on multiple GPUs. So if you have GPUs available, and you can do a configuration change over these cores of these frameworks, and they would still work for multiple GPUs, and that you can train it on. So all of that optimization can be done for those cases. If I hope that answers the question.
Yeah, yeah. I'll pick this one. That is, put up by Anuran again. What type of data sourcing would you recommend for scenarios when the data may get fuzzy?
Okay, so if this is for production systems, when what happens is uh, the data sourcing has its own strategy, right? How are you what So let's suppose if I'm talking about different users. I have 100 million users, and these users belong to different demographic, different culture, different language, everything. And I might need to make sure that I'm sourcing the data in a way which is the most efficient representation of the whole population, right? So the sampling becomes an important case. What sort of sampling I'm using. Like if I'm saying that I'm picking up every users from every demographic, every IP. I'm some users, I'm picking up only those users who are basically coming on the platform some particular number of times, like 5 active days or 3 active days or something, or some other sampling way. So all of these sampling methods come into play when you're trying to source your data for training your for training a model or any of the recommendation tasks. So those that sampling should be efficient enough, or able enough to basically make sure that it's a good representation of your overall population. Otherwise you may end up with training it for a certain population, and the other population will face a trouble, because the whatever the training or whatever the pipeline is built not built for them. So their recommendation might go bad, and you might assume that what possibly happened to your algorithm is not working or such. So sourcing a data becomes an important part, and that's a great question to ask.
Okay. There are a couple of more that we'll pick. So,
Sure.
what kind of stack database do you prefer in large scale recommendation engine?
So usually what happen if we talk about big tech companies, right? They have their own technology stack. So, but usually what if I'll talk in general open source audience, because most of 95% utilization of AML could be on other companies, right? They will mostly use open source stack. So if I want to use certain databases, like good ones should be starting with on the big data engineering side, Cassandra is an amazing database. It has good enough read write time, and it follows the cap theorem, which is there, like consistency, availability, uh, uh, that in a very efficient way. uh, Other than Cassandra, I would say HBase is also good. Using even MySQL simple databases could also work, right? If your solution is not for a big data solution, even a MySQL database would particularly do the job. So you don't have to go for Cassandra or HBase or such, these are basically big data ones, right? More or less from the deployment front, going for Redis caching or MongoDB caching, MongoDB storage for metadata and such works particularly great. So those are Redis or Meme cache or something like that, used for caching as a caching database, generally being preferred for storing your recommendations for some time, storing users requests for some time and such. So that you can do in that particular end. So I hope that
Okay.
answers.
Yeah. Also, yeah, I think a few of the past question putters have said that yes, I have dropped the thanks for your answer. I'll pick this question, which is slightly, I mean, it can be long in nature, but yeah, in the context of recommendation engine, do you have any insights on A/B testing as well?
Right. So usually, what I see is an A/B testing. A/B testing are like a very important part in recommender systems, right? What happens is, because usually, the algorithms, you don't know which algorithm will perform well for your platform, because largely these algorithms are more dependent on user behavior. So if you haven't understood user behavior correctly before doing a lot of exploratory data analysis, you might end up with having the best algorithm performing worst for a system. So A/B testing comes for the rescue in those cases, right? That you don't end up with such scenarios while you are building the algorithm, put all your efforts, and it doesn't even work on the platform. So having an efficient A/B testing system is a good way to go for. Usually, a statistical A/B testing are good approach, where you basically at least for the beginning on that platform, where you basically look for certain segment of your users, try it out for 1 month, that how this segment is performing on an algorithm, another segment of users trying another algorithm over there, and then you measure the performance of each of these algorithms over there. So having a statistical based A/B testing works, but they have a certain drawback, right? They are very fixed in nature. So you basically might end up selecting a wrong sample, and selecting a sample which is not a representative of the whole population, and then deploying getting a good bad insights about, okay, this model works, and then deploying it over the 90% of the other population which is not exposed to that model, and that model may end up not performing well. So all of that sort of change, that are challenges generally comes up when you do a statistical A/B testing. Now there are new approaches towards A/B testing that generally comes into, like reinforcement learning based A/B testing, like I was mentioning, like banded algorithm, which work in a stepwise way. So they look for reward functions, they look for agents, environments, everything, and they try to adapt based on it. So it's not just that your 90% is suffering because of those 5-10% that you tried or tested your model into, but it basically goes in a holistic way. So it basically makes sure that your recommendation and everything is being adapted and tested based on the feedback that has been received every time the model that the A/B testing platform test your model over the application, using a reinforcement learning or banded algorithm based A/B testing methods. So that those are basically the two areas. There are more elaborate discussion that we can do on it, but for the sake of time, we'll basically restrict it.
Yeah, I think we're done with our questions, and this is where I, thank you. But there's just one thing that I wanted to mention here before we, conclude this. It's on the lines of, so we did, just see about this particular session where we hosted Sumit. There are a couple of things that I want to share, and we'll definitely, we owe a big thanks to him. I think people have started in putting their, the thanks. If you're on LinkedIn, YouTube, DPhi, please feel free to drop your comments. It's definitely encouraging when somebody's putting in such a hard work to explain a concept from end to end and answer the questions even after we overshot by at least 40-50 minutes or so. We have this particular bootcamp coming up. This is one thing that I wanted to mention here. It is closing in tomorrow itself. So if somebody wants to get started on data science, they can check this out. And if somebody is into deep learning instead, I mean, you have the fundamentals right, NumPy, pandas, etc., then you should go for this one. Okay, and it will mostly cover neural networks, CNNs, GANs, LSTM, so on and so forth. um, Next week we have the exact same time, since it, deployment, we talked, Sumit mentioned about it multiple times. We have a live session on exactly the same, which is understanding machine learning operations, the why, the what, and a bit of how. Okay, so you can register for it. And yeah, we definitely owe thanks to Sumit, who has been super kind to answer all the questions. I just created a bitly link so that it's easy for you to follow on and remember it. So it's bit.ly/follow hyphen Sumit Jain. Do check out his LinkedIn, follow him there. And if you have registered on DPhi's website, we'll also drop you an email for the link for the session, along with the resource. I mean, along with his profile, so that you can follow him up for future updates. So do that for sure if you haven't done it already. LinkedIn is also good, but there we don't have your email ID, so we cannot nudge you in terms of the resources or his profile. And last bit, please follow DPhi on LinkedIn and subscribe to us on YouTube to stay updated for upcoming resources. So yeah, that's pretty much about it. Thanks again, Sumit. I mean, I kind of made a very formal thanks towards the end, but I'm genuinely thankful on the behalf of community for being so patient and elaborate in terms of explaining the concept. I think this was a very insightful one, and yeah, thanks a lot for being with us today.
Thank you so much, Mudit, and thanks everyone for having so much patience and staying with the call. And I really enjoyed it. So looking forward to have more interactions with you in the future. Thank you so much,
Yeah,
everyone.
sure, sure. Sure, the community would love to have you again. I mean, I can be pretty confident about it. But yeah, thank you so much. Uh, good night. Have a good afternoon and whatever applies to you. So thank you so much. Bye. Take care.
Thank you.